right. I come bearing geometry problems per request. So we're going to be starting on page 390. I cross-checked the old versus new edition of the book, and it does have the problems that I want. So we're going to be starting on page 390 in the Prep Plus Blue Book, and we are looking at problem number 2. And that one is dead. Where's the garbage in this room? Ooh. Not worth it. So, we have two circles, one within the other, and we're told that this one is distance of 4 feet. It's interesting that they give feet, but even the multiple choices don't say feet, it just says area in square feet within the question. So the radius of the larger circle is 75% greater than that of the smaller circle. And we are asked for the area of the shaded region. The calling out of names seemed to work pretty well, so go ahead and begin, if you have not already.
Monica.
Thought somebody had started already.
Soren. John Paul. Christian.
All right.
B.
So, adjusting teaching style for the age group and their skill level.
Is this your work?
Yes. You are probably already aware that if you want 75% greater, easiest way is to take 4 and multiply by 1.75. The 1 will compensate for the original, and the 0.75 is the greater. And 4 is a lovely number that the 0.75 works into a nice pretty number. What is our new radius? Didn't think it was that hard a question.
7, right?
7. And so, again, keeping those nice lovely numbers allows them to have nice pretty answers. And so all we have to do is take the difference of the two areas. We're going to have 7 squared pi, or 49 pi, minus 4 squared pi, or 16 pi. 4 minus 1 is 3, 9 minus 6 is 3, 33 pi. All right, go ahead and look over at number 3. This one's going to be a little bit more difficult, and this is one that I'm very, very grateful that it's in your book, because I did not want to try and copy this down or explain it to you. Diagram pictures are one thing, but the words, that's something else.
Monica. What page on the book is it?
This is page 390 in the Blue Book. It's got a question about the Earth making one complete rotation about its axis. Glad to hear it.
Christian.
All right, so the breakdown of that block of text is that the Earth does a complete rotation every 24 hours. There is tiny variations, but not enough to talk about. So in 24 hours, it makes a complete circle around, or 360 degrees. But we are talking about January 1st at noon to January 2nd at 3 p.m. So the first thing you need to be aware of is that this is 1 day plus how many hours? 3. We start at noon, we go to 1, it's 1 hour, get to 2, it's 2 hours, get to 3, it's 3 hours. So 1 day plus 3 hours. The 1 day, just keep as 360. It'll make your calculation numbers a lot easier. The 3 hours is 3 hours out of 24, or 1/8 of a day. And so we need 1/8 of our 360, and we get 45 degrees. 360 plus 45 will equal 405. Questions on that one? About the right difficulty? All right. Go ahead and jump to page 394, number 4. Number 5 is one that we did last time, but number 4 is also a good one. Again, I'll start doing some sketches up here, but you work on your own and call out names when you're ready.
Is this the purple book? The Kaplan one?
Yes. This one?
Okay.
Like I said, I've got a different edition, but I'm looking at hers and seeing that it's close enough that I'm able to still use these, which is making me happy. Because it's always better if you can read it. would you like more time, or would you like me to start giving you hints on where to get started? All right, people are finishing up. All right. Since we have a square, we can find the side length by taking the square root, and it simplifies to 2 square roots of 3. Since we have an equilateral triangle, this is a 60 and 90 and 30 triangle. What do we know about the sides of a 30, 60, 90 triangle? They're not equal, but they do follow a particular pattern. So if this is our 60, this is our 30, and this is our 90 degree, the sides follow the pattern where if this is x, this is 2x, and this is x times the square root of 3. The 2 and the 1 are very pretty and useful, but this one is still okay. But we already have our middle side, or the one across from 60, in the form of 2 square roots of 3, which means our x would just be 2, making this 2 and 2. Since it's an equilateral triangle, we only need one side, and then to multiply it by 3. Don't forget to multiply because they ask for the perimeter. And so 2 and 2 make 4 plus 2 square roots of 3. And if we multiply by 3, we get 12 plus 6 square roots of 3. So, reminder on those special right triangles. They show up quite a bit. All right, go ahead and flip to page 405. All right, we'll go ahead and do number 1 to start with as a little bit of a warm-up.
Sorry, can you repeat that? What problem are we in?
So we are doing number 1 on page 405. It's got this goofy cross triangle thing going on. And we are told that this is 100 degrees, this is P, and then in the words they tell us that N is the intersection of segments MO and LP, which is pretty much obvious from the drawing, but they say if the measure of LM, LM is congruent to MN, is equal to NL. Oh, I just jumped the gun a little bit. So all three of those are the same. What is the measure of NPO, or this angle up here at the top?
Monica.
Soren. Christian. You.
So, again, they are really, really fond of equilateral triangles. There's just so much that can be done with them. Both the idea that equilateral means equal angle, the idea that those angles are 60 and therefore you can work with the special triangles. They really love their equilateral triangles. This is equilateral, making all the angles also equal. In other words, this angle is 60. This angle is 60. This angle is also 60. And that leaves only 20 left for that angle at the top, because it's a triangle and has to add up to 180. All right. Go ahead and jump back to page 404. It's just on the opposite page there. It's got layouts with different furniture. It says, Lorenzo is deciding between two examination room layouts for his new clinic. The cross-sectional area of each square chair is 2 square feet, and the cross-sectional area of the circle chair and the exam table are pi and 4.9 square feet respectively. What is the difference in the areas in square feet of the shaded portion between the two layouts? And if you don't have your book with you, I'm just going to hold that up there because I don't feel like drawing that.
Sorry, can you hold up?
One more time? Sorry.
Okay, thank you.
Monica.
Christian.
For those of you still working, you're gonna hate me. So this problem exists. If you look at the top, it says occasionally a question will give you more information than you need. So looking at this problem, what is the only difference between those two rooms? The desks. The only difference between those two rooms is the desks. Everything else is the same. And so the area of one desk is 10 square feet. The area of the other desk is only 8 square feet since it's a triangle. And what's the difference between 10 and 8? Just 2 square feet. And so before you leap into, oh, I have to find the area of this one and add it up and everything else, it is the same. All right. Number 2. Again, this one should be a little bit faster. It says the ratio of the perimeters of two similar triangles is 4:7. And the sides of the larger triangle are 10, 12, and 13. And it asks for what is the perimeter of the smaller triangle.
Christian.
Somebody brave, just yell out, what is the answer?
20.
All right. So, number 4, this one is a little bit more difficult again, now that we've done some warm-up geometry type stuff. It says the figure below shows triangle WXY in which Z is the midpoint. Z is midpoint of WY, and WX is perpendicular to YZ. Sorry, YX. And the question is, what is the length in inches of WZ?
So I.
All right. The single hardest thing about this problem has nothing to do with solving the problem at all. In fact, that's the problem. This line makes me start second guessing of, am I supposed to be doing something with it? And the fact is, no, it's just drawn in there to be annoying. We need to know that Z is the midpoint, in other words, these two are the same length. And we need to know that this is a perpendicular, or we have a right angle. We've got a right triangle, and we have our two sides. If you run it through your calculator, honestly, it's fast enough. That might be the fastest way to do it, but it also happens to be a Pythagorean triple. Back to the idea of 3, 4, 5. 18 is 3 times 6. 24 is 4 times 6. 5 times 6 would give us a length of 30. And then half of 30 is 15. But again, I wouldn't waste too much time trying to recognize that as a Pythagorean triple if you didn't right off the bat. Calculators are fast enough. Typing it in is not that big a deal. All right. That's the last of the problems from the dedicated geometry section. Oh, no, there was one more. So if you flip the page to 407, look at number 10. apologize for my lousy drawing skills. The image is not to scale. So, in the figure, point C is the center of the circle. Again, apologize for my art. And the measure of angle D is 37 degrees. Which of the following expresses the length of the radius? And our options are given as 15 on all of them. But we have sine, cosine, tangent, and the question is
Monica.
Can be sine. Vision.
all right. Which one is it? Everybody's shy. So, we are dealing with 15. We know that's the hypotenuse of our triangle, and so that cuts tangent right out. If we look at the cosine of 37, that would be this length right here, not our radius, and so that one is out. And then finally, we're looking at the sine, or across the way from our 37, and this is the one we need. All right. Taking it just a little bit differently. I don't know that you've done this before. So I want you to look at page 408 and 409. So, don't be afraid of being wrong, but if I asked you, how can you tell whether two triangles are similar? How do we know when two triangles are similar?
Same angle measures?
The same angle measures. And so the same angle measures are what lets us use that proportionality. And that's something that they're really fond of using. The other one to be aware of, I just did it with my class there. When you've got this set up and they tell you that they're parallel, that lets us have the same angle measures. Because if you completely ignore this side, these are parallel lines cut by a transversal. These angle measures are the same. These are parallel lines cut by a transversal. These angle measures are the same. And then obviously that's similar to itself. And so parallel lines letting you have those similar triangles will also let you set up the proportion. And so that one is one that shows up a lot within geometry. So number 2, what are the two Pythagorean triples you're most likely to see on test day? Alright, switching up the question, what's the one Pythagorean triple you are most likely to see on test day? 3, 4, 5. The other one, honestly, for me, it's a toss-up. They are also really fond of 6, 8, 10. But the other one that shows up frequently is 5, 12, 13. And so those are the ones that I would be most aware of as Pythagorean triples. Like I said, that other problem technically was one, but to me, the time it took me to recognize it as a Pythagorean triple, it was just as fast to enter it into a calculator. So those ones, be familiar with them, but other than that, it's pretty much just a calculator work. Also 9, 40, and 41, but that one's less obvious. What are the ratios of the side lengths of a 45, 45, 90 triangle and a 30, 60, 90 triangle? That ties into the problem that we just did.
Might just be 1, 1, 2 for the first one.
Not 1, 1, 2. Close. 1, 1 square root of 2. Because if it was 1, 1, 2, we've got a straight line, not a triangle. And then our 30, 60, 90, we have 1 square root of 3 and 2. And again, these can be times any x. So anything. We could have 5, 5, 5 square roots of 2. We could have 13, 13, 13 square roots of 2. It just follows that pattern. And then here we have 1x, x square roots of 3, 2x. So places that you will see these show up. This one, they love equilateral triangles. They will use those all the time. They also really like hexagons. Because if it's a regular hexagon, that's going to be an equilateral triangle. And so they'll hide it in that one. With these, most commonly half squares. Because if it's a square, these two are the same, and that one is the square root of 2. So those are where the 45, 45, 90 triangles show up, and the 30, 60, 90 triangles show up. So when doing unit conversions, how to make sure you're doing them correctly. So, when doing unit conversions, the best way I can tell you is make things in the top and the bottom so that the units cancel out just like other numbers would cancel out. And so if you're converting from inches to feet and from feet to miles, you want the feet to be opposite each other so that the feet cancel, and then you have inches and miles. And so the idea that 12 inches equals 1 foot and 5,280 feet equals 1 mile, that is how you find out how many inches are in a mile. And so if you need help with those units, just make sure that they're staggered top and bottom so everything cancels except the things that you want. All right. What is the relationship of the circle's central angle to the arc and sector of the arc? I can't talk. The arc and sector the angle defines. So what that's talking about is if we have a circle similar to that Earth rotation problem, and this is x degrees, how does that relate to this arc length and this area? Looks like a really bad pizza. You did it because you got that question, but I'm not sure that you understand the words that it's asking. So the important thing is, we're going to take this x and divide it by 360. And that's giving us the fraction of the circle, or the fraction of the circumference. So if you need the arc measure, you're going to take this fraction and multiply it times the circumference. If you need the area, you're going to take this fraction and multiply it times the area. And so by taking that degree measure and dividing by 360, you're finding out what fraction of the circle you have, and that allows you to find the arc measure or the sector area. And so feeling confident about comparing it back to the whole thing of 360 is the fastest way to get those. All right. Lastly, this one's more of a conceptual problem, but again, a good one. It says, how would you find the surface area of a right triangular prism with equilateral triangles as its bases? So, a right prism is one that's going to be standing upright when you set it on its base rather than being skewed sideways. And so that's all that means. And we have equilateral triangles as the bases. Here is our right prism. And again, this is meeting at right angles with the base, is all that right means. So how would you find the surface area of this shape? This one I am going to wait for name to be called out. It doesn't say, but I'm assuming that you would know a side length, if that helps. And I'm assuming you would also know the height of the prism, because those would be required.
Wouldn't the side just equal the side of the rectangle?
Okay, so the sides, if we draw this as a net shape, we're going to have 3 rectangles, all with lengths of the side, and then 1 triangle up here and 1 triangle here. Again, these are the same as the sides. And our height will be that height. So the rectangle wrapping around it, yes, that's very easy. It's going to be 3SH. And that's this area. Good. How would we go about finding the area of those triangles?
Would just be a half.
Close. You're getting there. What is the area of a regular triangle? Oh, we found the missing point. Okay. Let's go back to the very beginning on that. We've got about 5 to 10 minutes. We'll make it work. So, most basic area. Square or rectangle. We're going to go with the rectangle. The idea is this is length times width, sometimes known as base times height. most basic triangle is half of that. And so a triangle equals 1/2 the base times the height. If we go a little bit more complicated than that, this is still 1/2 base times the height, because we have half of this rectangle and half of this rectangle. And so altogether we have 1/2 the base times the height. And even if you've got a funny isosceles slanty triangle like this, it actually still is 1/2 the base times the height. So that is our area of the triangle. So on this equilateral triangle, I'm going to borrow this one, we only know the base, this length S. But back to the idea of being equilateral, it is equiangular. We've got that 60 again. And from here we can treat it as that special right triangle, or you could even do trig with it, whichever makes more sense to you. But if this is S, this length is 1/2 S, and our height is 1/2 S times the square root of 3. But we have 2 of them. And so for our total triangle, we can go back to our base being S. So we have 1/2 times S square roots of 3 times S. This is base times height. Normally we'd have to multiply this by 1/2 again, but that's going to cancel because we had 2 triangles. And so that is our thing. It's a little ugly. I'd simplify it to 1/2 S squared, square roots of 3. And we would add that to our 3SH. Huh. Did not expect area to be the Achilles heel. I've been going too tricky on the geometry stuff. All right. What was the other one that I wanted to do with you guys? All right, so back to this triangle with the parallel line cutting it. We are told that this is 4 units and this is 12. They tell us that this small triangle area is 8 units squared. And the question is, what is the area of the large triangle? All right, somebody from online wave at me just a little bit because I'm terrified that you've frozen. Thank you.
Top up.
Okay. All right, the first question I'm going to ask is, how long is the side of the large triangle?
16.
16. So it's important, anytime they want to talk about a combined total, they'll use something like these brackets or a span distance where it looks like this and it has the number in the middle. And so the 12 is referring to only this piece. So from 4 to 16, what is our scale factor comparing these two triangles?
Times 4.
Times 4. So 4 times as big. So scale factor equals 4. How does scale factor relate to area? If this is 4 times as long, is my area going to be 4 times as big? So, John Paul's a bit of a ringer because I did this with him over the summer. If we double our length of our square, this was 1, now it's 2 and 2. Our area is now 4 times as big, or the 2 squared. If we triple our area, and it's now 3 units by 3 units, our area becomes 9 squares, or 9 times as big. And again, that comes from 3 being our scale factor squared. As you increase the length, the scale factor of the area is going to be that scale factor squared. And so if we go from 4 to 16, our lengths are 4 times as long. Our area is going to be our scale factor squared, or 16 times as large. And so we will take that 8 and multiply it by, I'm not sure what I'm saying, 32, 16. And I believe it's the 128. So, if they give you lengths and they ask about the comparison of area, you're looking for the scale factor between those lengths, but you end up squaring it. And if you get a volume problem, which are less common but still possible, the volume will be cubed. And so if this were a 3D prism and they had the scale factor multiplying each side by 4 in all 3 directions, it would be 4 to the 3rd power, or 64 times as big. So scale factor and volume and scale factor and area are related, but they are not exact. They're not an exact match. That would work if we were only increasing in one direction, but not both. All right, we are out of time. I said I was going to do 50% geometry. I did a little bit more than 50% geometry, but I don't think you minded too much. All right. So, did Manoj go over calendar with you guys? Okay. Reminder, there is no class next Sunday because of the Thanksgiving break. And when you come back the Sunday after that, there is the writing prep portion, And if you signed up for the essentially ACT test run, that will be on the Saturday before the last class. And so those are the dates to be aware of coming up. All right. With that, I will say goodbye and thank you for being an excellent class as always.
Thank you.
Bye.
Thank you.